Alright, in this video we're going to cover basically chapter 4, and we're going to go through some right angle trig. So in section 4.1 we kind of go through and talk about different types of an angle. Not different types of angle, what angles are and how they work with the unit circle. So this video will go through with my OneNote lectures so you can kind of follow along. So an angle is generated by rotating a ray about its fixed endpoint from initial point to a terminal position, right? And if we rotate is counterclockwise, the angle is positive. If clockwise, then the angle is negative. Right? So these are right out of the book. So draw the figures on page 114. So we have a point, and if we draw our initial side with a ray, and then we draw another ray at the same point, that becomes our terminal side. And this is known as the vertex, the turning point. So if we go counterclockwise, so we go open up to the left, then that is a positive angle. If we go clockwise and we open up to the right, then that is a negative angle. But you can see both finish on the same terminal side. It just depends on where you measure the angle from. So just to kind of remind us, if I put an XY coordinate in black here, and we start at 0 degrees and we go counterclockwise, our green theta, that's the symbol is the theta, which is just a symbol for an angle, it's a Greek letter, is a positive angle, and it's somewhere in quadrant 1, so that is called a first quadrant angle. And if we open all the way up past 90 degrees and go into the second quadrant, which is our orange, then that is considered a second quadrant angle. And our third example is we start and go all the way through the purple, and then that is our third quadrant angle. Right, and I didn't draw a fourth, but if we come over here, then that would be a fourth quadrant angle. I think everybody kind of gets the idea of how these things open up. And these are all positive because they're all going counterclockwise. And again, I can go clockwise, but most of the time we go counterclockwise. So a coterminal angle has the same initial and terminal side. Basically, what you're doing is it's kind of like an equivalent fraction. It's not, you're adding to it, but it's not changing anything, right? So say we have a coterminal angle of 45 degrees, which could be very similar to our green angle right here, right? And if we go in a complete circle and bring it all the way back around, we're still at the same terminal side, right? So if I take 45 and I add 360 to it, I get 405 degrees. So I've gone all the way around. So a coterminal angle of 45 is 405. But I could also go the opposite way. So if I start at 45 and I go clockwise and bring myself all the way back to the terminal side. Notice I don't make a complete circle. I do make a complete circle, sorry. I started here, not the initial side. Terminal side, I do make a complete circle. But I go clockwise. So I take 45 and I minus 360 degrees, and I get an angle of negative 315. And remember, it's negative because I went clockwise. And I can keep doing this over and over again and making as many coterminal angles as I want. And then our degrees and our angles are all kind of based on the unit circle. So I gave an example of the unit circle here in the notes just for people for reference. We don't do a lot with the unit circle in this class. However, if you take pre-calc, you'll kind of really dive into it. But what is interesting here is inside the unit circle, we have our degrees, which I had drawn above, our 0, 90, 180, 270, and it brings back around to 0 or 360. So 360 degrees in a circle. And then our numbers just past the degrees are what we call radians. And they are written in pi form. So you can see 90 degrees is the same as pi over 2 in radians. So we're going to talk about this and making sure your calculator is in degrees and not radians. You can put it in radians if you choose to, but then just make sure you know how to convert everything. So remember, 1 degree is 1 over 360 of 1 complete rotation, right? Because that means it'll be like tick around the unit circle. So converting radians to degrees, this is more in case you want to, but most of the time we'll take our calculators and just convert them into the proper thing. But 1 radian, 1 rad as we call it, equals 180 degrees divided by pi. Sometimes you'll see the pi symbol in the answer, like you see in the unit circle, and sometimes you'll just use pi in your calculator, which is what we did in the first example. So if we have 1.36 radians, and I want to turn that into degrees, I take 1.36 and I multiply it by 180 degrees divided by pi. So 1.36 times 180 divided by pi, and actually use the pi symbol on your calculator. Don't do 3.14, it's rounding too much. So I actually found the symbol on my calculator for pi and hit divided by pi. You get 77.9 degrees. So that's how you go from radians to degrees. If I want to go from degrees to radians, say I have 145 degrees, that equals 145, and now I flip it. And how I know how to flip it is, if I want the degrees in the answer, then 180 needs to be on the top. If I want to get the degrees out of the thing, then the 180 needs to be on the bottom. So 145 times pi divided by 180. So 145 divided by 180 is 0.80555 repeating, so I rounded it to 56. And then I left the pi symbol in. So one answer is 0.8056 pi. If I don't want to leave the pi symbol in, then it's multiplied by pi, and I get 2.53 rads. So this is how you can convert by hand. However, there'll be a couple of problems in the homework, but most of the time our calculators will be set, so we don't have to worry about it. Now, what you might have to do is converting, right? Because typically degrees are not written in decimal form. So 1 degree is the same as 60 minutes, this little tick. And if I have 2 ticks, that's 60 seconds. The good news is it's kind of like a clock. You think it's degrees in an hour, 1 hour, 60 minutes. And then every minute there's 60 seconds. So it's conversions of 60. So if I had to put 17 degrees and 53 minutes into my calculator, I need to convert it into a decimal. Well, the good news is just turn it into a mixed fraction. So 17 is the whole number, 53 becomes my numerator, and my denominator is the 60. So 53 over 60 equals 17.88 degrees. Now, how this all plays into trigonometry is now we're going to start using the xy axis and drawing some angles. So I drew my x and y axis in red, and if my initial side starts on the positive x-axis, so we start at the origin, just like we do with graph, and we draw a ray out to the right along the x-axis. This is our initial side, right? And then we draw our terminal side. So in this one, I put it in a second quadrant, just to see. So this is a second quadrant angle. And I have some point out here, xy, and I draw my terminal side right through that point. And now I have created an angle where the vertex is at the origin. And then again, here is my theta. R is on my terminal side. And we have our angle. And what type of angle is this? This is an obtuse angle because it's greater than 90 but less than 180. So this is how we're going to use the xy coordinates to create some triangles here in this video. And just remember, we always start at the origin, and our initial side is the x-axis, and then we create an array from our vertex of wherever we want it to go. Which brings us into our trig functions. So the trig functions we're going to learn are sine, sine, cosine, and tangent. And then their inverses, as we call them, are cosecant, secant, and cotangent. And this is all on page 117 in your book. And so what trig's very useful. I always like to joke that trig is kind of like algebra and geometry mix. So if algebra and geometry had a kid, it'd be kind of like trigonometry. And we have a class here for just trig. So we're only going to get into a little bit of trigonometry, just right angle trig in this class. But things that use trigonometry, anything where you are going to use angles in, say, so trajectory of a baseball or a football, anything you can kind of throw can be done through trig. Right angles, if you know the sides, then we can use the Pythagorean theorem as we have here in our notes, right? Remember, Pythagorean theorem is a squared, b squared, and c squared. But what if you know what angle you want and you want to figure out how long something is? And that's kind of where trig comes into. So it's used a lot in building, carpentry, engineering, and in our class, like I said, we're going to stay, everything's going to be based on a right angle. And remember, a right angle just means the triangle forms, the angle has, somewhere in the angle is 90 degrees. So we will just stay in right angle. So anytime you're doing any problem, remember, it has to form a right triangle some way, some form for us to do what we're doing in this class. So sine of theta, that's the Greek symbol here, right? So the sine of some angle is equal to the ratio of y over x. Right, so these are all ratios. And what we use these for is basically not to be able to do things in our calculator or to solve for sides, because your calculator will actually solve this for you, right? So you got to remember that this is kind of, you're going to use these to solve for unknowns. That's how we're going to bring algebra into this. So let me just do an example so we can kind of see how this all comes together. So I have my x and y coordinate, right? And I'm going to draw what we call a 3, 4, 5 triangle. So let me draw in red here. There we go. Oh, I gotta change my color here in a minute. Change that to red so we can all see the differences. There we go. So we have our 3, 4, 5, and I got a right angle. So there is my right angle, right? And again, we know it's a right angle, because if I put a little kind of like that right there, shows that it is a right angle. And I'm going to complete my triangle. We'll stay with green. We'll draw our little terminal side in green. All right. So there's our little triangle, and a horrible drawn right triangle to show that's the right triangle. But 3, 4, 5, basically I'm saying this goes through the point 3, 4. I don't know why we're underlining, so let's get rid of my underline there. We go through the point 3, 4. So that means, trying to type it so it's a little bit neater here. That it goes up to 4, right? And it goes to the right. Again, I'm underlining for some reason. I don't know, my thing just defaults to this underline all of a sudden. Sorry, OneNote just doesn't let you click where you want to type, unfortunately. And it goes over to 3. We'll go one more here. Try this again. There we go. So it goes over to 3. So my x is 3. So 1, 2, 3 spaces over. My y is up 4. So that basically means my initial side has a length of 3. And this our vertical line here has a length of 4. And then where the 5 comes in, let's go back a little bit. That is our r. So let me put some equals here. This is our r. This 4 is equal to our y, and this 3 is equal to our, not 3, it is equal to 3 our x, right? So now if we use the table, if I want to find, and again we need our theta, so let me copy this guy. Let's make it a little bit smaller. So all right, there's our angle theta. I can then do these functions. I'll do it here just so I don't have to mess up on my drawings. So if I want to know what the sine of make all this the same font here. The sine of theta. And according to the table, that is y over x, so that is just 4 over 5. No, sorry, 4 over 3. Y over x, remember x is 3. If I want the cosine of theta, that equals x over r, so that is 3 over 5. And then lastly, if I want the tangent of theta, that equals y over, oh, I got a typo here. Cosine is y over r. I don't know how, that should not be an x, that should be an r. So I was right the first time when I said 4 over 5. Because tangent is y over x. So that is 4 over 3. So I fixed my table. So I'm good at making this video. I had notes. I had a typo in my table. So the sine is the y value over the hypotenuse, r, right? Cosine is x over r. So both of cosine and cosine are over the hypotenuse, while the difference is sine is y, cosine is x, and then tangent is just y over x. Now, if I want to find their inverse functions, so cosecant of theta, oops, command V, no. Well, that will equal y over r, and basically it's the inverse. You just flip it, so that becomes 5/4. And if I want the inverse of cosine, which is secant of theta, then that is, again, you just flip it, so 5/3, or r over x. And then finally, our tangent is cotangent of theta, which is 3/4. Flip it, or x over y. So we'll bring this guy into our table here. So it's easier to see on one screen if you look on this on a tablet. So there is using our table, right? And I can prove all this works by applying the Pythagorean theorem, which is what most of you are going to like because it's just what you're familiar with, so you've seen it, right? Because the Pythagorean theorem says a squared b squared, and we'll just do it right here. A squared plus b squared equals c squared is another way of saying this. This is x squared. I'll have to turn math on here in a minute. X squared plus y squared equals r squared. Let's clean this up a little bit. So I want that a lowercase x. There we go. There we go. So you can write it using different variables. Remember, all the variables is an unknown, so it doesn't matter which letter you use per se. So now I can take this and show that 3 squared plus 4 squared equals 5 squared. Or math, just to clean it up so the symbols look right. I don't know why I did that. Undo. Put this on a new row. There we go. Equaling each other. Sorry, the video goes a little slower with me actually explaining. I figured it'd be better if I just work through it like a lecture than having it all typed out for you just reading. So if we do this, this is 9 plus 16 equals 25, and 5 squared equals 25. So these sides are all correct. Now, so some of you will be like, okay, what is the point of all the trig then? Well, what we didn't do is we haven't solved for the angle, right? We don't know the angle. We've only found is the sides. So what trig will help us do is now find out exactly what angle theta is. Right now I'm just trying to show that these formulas are all true, right? So if I double my values, right? So say my 3, 4, 5 triangle, my x is now equal to 6, and my y is now equal to 8, and then r is equal to 10. If I go to find the sine of theta, well, that equals, again, make sure I don't get it wrong this time, go back to our table just to help me confirm, y over r. So y is 8 over r, which is 10, which reduces, when I simplify the fraction, reduces back down to 4/5. So theta is not going to change because the ratio didn't change. All I did by doubling this is move the point from 3, 4 out here to 6, 8. So all I did was increase the sides, but I didn't change the angle because I'm still on the same terminal and initial side, right? So another example here is, what if we only know one thing? So say we know cosine is 4 over 7, and we know it's a first quadrant angle, which means it's in the first quadrant. Can I find everything else in my table? Right? So, again, here's my xy coordinate. And let's see if I can draw here. We will come down here and get the right things I want. Nope, I don't want that. I want that one. Okay. Oh, why is this not doing what I want to do? Come on, draw for me. Thank you. So we have this, we know we're in the first quadrant. So I'm going to do my 4, 7 here. And I'll do my hypotenuse in red. Oh, I think I just changed my thing into red. There we go. Definitely going to get better with using one note in my drawings. There we go. Draw. Color. Jeez. Might as well keep the same color. So I got my triangle. So again, if this is 4, 7, right, I'm just going to write it this time to save time. So my x is 4, and my r is 7. That's all we know, right? Can I find all my other functions? So we know, we'll build our little table here again. So actually, I'll just copy this one to be quicker. C. Actually, no, I have it all written down here, so we don't have to do all that. Undo. So first thing we got to find is our y. So we used our Pythagorean theorem. So 4 squared plus y squared is 7 squared. So 16 plus y squared is 49. Subtract 16, I get 33. To get rid of the squared, I take the square root. So we can add that little line here. We can see it. So basically I subtracted 16 from both sides. So y squared equals 33. Again, that's supposed to be a little y. Right? And then to get rid of the squared, I take the square root of both sides, and I get 33. So now I know this is the square root of 33. Now I just apply all my ratios, and I can find all my sides. So remember, sine is y over hypotenuse, so the square root of 33 over 7. Secant is, oh, I wrote these in the wrong order, but that's all right. We'll move him just so they're together. Command X. Cosecant, which is the inverse of sine. So I flipped it. We knew cosine was 4/7, so now our secant, which is the inverse of cosine, is 7/4. And then there's our tangent and cotangents. So that basically takes us through 4.1. 4.1 and 4.2, sorry. So now we kind of get into 4.3, which is dealing with the angles. So if we know the angle, can we find the initial terminal and the side opposite of the angle? So we got our common angle of a 30, 60, 90, right? Remember, a triangle sums up to 180, so 30 plus 60 is 90, and again, our 90 is our right angle, so this is a common right angle, 30, 60, 90. All right, so let me fix this up here. So draw on the board, letting y equal, solve for x. Okay, and I already did that. So let's give us a little space so I can show you how this all works out. So draw. So first I put on my xy coordinate plane. And now I'm going to draw my triangle here. So we're drawing a right triangle again, starting at the origin. I don't know why I just did there, so I'm going to undo that. It might show I'm not even drawing this scale because I'm just trying to draw it neat so you can actually see it. So I'm just scribbling all over the place. So now, if we know use green. If we know this angle is 60, degrees, and this angle is 30 degrees. And then again, we know this angle is always our 90. And we said that y is 1, so this is a 1, and r is 2. Then we can find x, right? Because we have x squared plus 1 squared equals 2 squared. So x squared plus 1 equals 4. Subtract 1, x squared equals 3. And then we take the square root, and that's where I get the x equals 3. Drawing on my iPad here to make it look a little bit neater. It's messed up my drawings here. So that's why I hate doing the draw method sometimes, because it doesn't line up as well. So so we make sure we're in degrees. So we now want to find the angles. So we know, based on this, that's why I was typing before, so we'll just type again so we don't lose it. Command V, sine of theta equals y over r, so that equals 1/2. So we know the sine of theta equals 1/2. So I want to prove here that these are all related. So if you go to your calculators and you find the sine function and you put in sine, so hit the sine key on your calculator and then put in 30 on your calculator and hit enter, you get 1/2. And if I take the cosine of 30, and you can do all of the tables and see that these things work. So now there's also a key on your calculator that has a -1, and it's typically right above the sine, cosine, and tangent. These are not the inverses. These are not the secant, cosecant, cotangent. These are how you find angles. So if I go to hit my calculator, it's shift, right? So it depends on what kind of calculator. It might be mode or something, but so shift. So I get sine -1. And then I put in 0.5 for 1/2, I get back the 30. So this is the key. -1 on your keys are how you find the angles. When you sine, cosine, and tangent on your calculator, that is how you find the ratios, which are the exact same thing as what is in the table on page 117. All right. Okay, so what if we have to find something, say the cosecant of 48.44? Well, cosecant is not in your calculator. So if I take the cosecant of theta, remember cosecant of theta is the same as 1 over the sine of theta. So theta is the same angle. So if I have sine of 48.44 and I go to my calculator and I type in sine of 48.44 because it's the same angle, I get 7.748261. Now, if I take 1 over the sine of 48.44, so 1 divided by the sine of 48.44, I get 1.336. And I also can do 1 divided by what it was before, 0.078261. And I get the same answer, right? So, because we know that's 1 over, then cosecant has to equal that same thing. So that's how you could find out what the cosecant equals versus when you don't have a calculator. So I'll create another video for sections 4 4 and 4-5, which is its own note in one note, because this one's also been pretty long. That way you can kind of take a break. In the next video will be called completing a right triangle. All right, so all my notes will be saved with all my drawings. Email me if you have any questions. Thank you.